This episode is brought to you by Cisco Educational Premium.
Our universe is made of math. This is rather a bold statement, but just to say that mathematics describe our universe fairly accurately, say removing the inconsistencies and undefinable concepts of it. When we scan down the particle realm, the quantum level, we see that the existence of every particle can only be defined mathematically. Probability theory dictates the chances of a particle being present at the quantum realm and even the nature of it. The perspective of the observer is also crucial, as the nature of the particle depends also on the observer, or basically the measuring instrument, so to speak. So, you might be looking at a blue cat while someone else might be looking at a green cat. And here, the cat is still the same one cat. I know this might seem counterintuitive, not easy to understand, and yes, it is. No wonder Albert Einstein was confused, affirming God does not play dice, to which Boho answered, "Hey man, don't tell God what to do." Yep, badass. This stuff is actually very trippy. I don't even know how I'm able to comprehend this. Most of the math in high school got me like, huh. Okay, great story. Back to the show. So, where are we again? Okay, I was explaining how math is ingrained to the fabric of reality, and you were trying to understand. Okay. In mathematics, there are tools called equations, specifically differential equations, that aid and are the chief tools in describing reality. So one of these tools, and I quote, is the Schrodinger equation. Schrodinger equation is a linear partial differential equation formulated by Erwin Schrodinger in 1925. It describes everything we need to know about a quantum world. However, it has some drawbacks. The behavior of a quantum wave function is described by Schrodinger equation, which tracks the quantum wave function's evolution through space over time. As we learned, the Schrodinger equation is a linear partial differential equation, which basically means that if you add together solutions to the Schrodinger equation, the result is also a solution to the equation. This is part of what makes superposition to be possible. It allows different parts of the wave function corresponding to different measurement results to evolve independently of each other. Something else about this guy is its time reversal symmetry. Running it forwards generates future states. Also, running it backwards allows you to recover the past states. This means that quantum events which are reversible, instantaneous, and non-local cannot be modeled successfully. For instance, the wave function collapse. To fully build a universe where all the quantum events are fully accounted for, even to the classical level, every particle should be accounted for as well as every interaction it will have with its environment. There is an equation that can do this efficiently, at least for most cases, and this is the standard model Lagrangian. The standard model Lagrangian is an equation that describes the behavior of every known particle in the standard model, hence the name. So if we are able to keep track of every known particle together with their interaction, we can then have sufficiently enough stuff to build our universe. So where do we start on this standard model Lagrangian? The key is this Lagrangian thing. So let's look at it. This all possible due to a very useful concept in physics called the principle of least action. It is an alternative model to Newtonian mechanics. So don't sweat about it. It tells us that nature will always act in such a way to minimize the rate of change of a quantity called action. The Lagrangian is the path of the action quantity that we work with. Classically, it is the kinetic energy minus the potential energy. If we substitute the Lagrangian of a system into the Euler-Lagrange equation, the result will be the equations modeling the trajectory of the system. This Lagrangian is powerful because it respects symmetries. If the system has a particular symmetry, then the Lagrangian will have the symmetry too. By applying the principle of least action to the continuous symmetry, we will reveal the existence of a conserved quantity like energy or momentum. So what we do here is that we will just figure out the Lagrangian of a function that have our symmetries of interest, which is our equation, the standard model Lagrangian. It is pretty badass mathematical tool that will solely, for most part, aid us in building the universe. The standard model Lagrangian is quite complicated. It has several terms that each account for different ways that the particles of both matter and force interact, and each of these terms is a short for a lot of other things. Keep in mind that we are trying to model the particles in the standard model and their interactions with each other. Particles can have two different types of spin, as we had seen in an earlier episode. They can either have an integer spin like 0, 1, 2, 3, 4, etc. Or they can have integer spin like half, 3 on 2, 5 on 2, and so on. The spin determines what is probably the most fundamental nature of a particle, whether it represents matter or force. Particles with integer spin are called fermions, and they are what constitute the matter we have in our universe. Particles with integer spin are called bosons. They transmit energy and momentum according to the symmetries of each force. Some parts of the standard model deals with bosons, other parts deal with fermions. Others deal with interactions between the two sets of particles. Now, we have all what we need to look at our weapon of creation, the standard model Lagrangian. First, we have this first term that is opening our equation. The gate, if you say. This is known as the kinetic term, and it tells us how the boson will behave and how they will interact with each other. It describes the universe with no matter whatsoever. Those F's are actually shorthand for the separate interactions of each of the three quantum forces. First, we have the photon field, usually represented with a capital A. It is the field that serves the U1 symmetry of the electromagnetism, and the kinetic term for photons is made up of derivatives of the A field. This is like the energy of photons as they change in space and time. This is true for all the derivatives that we are going to see. They are analogous to the kinetic energy of that object in every direction in space and time. This is why we have the mu and nu symbols. The kinetic energy of the field in one direction may depend on what is happening in the other direction, meaning we need to take derivatives of the field in every direction. Instead of writing each one, we just write these symbols, which basically means we do in the x, y, z directions of the Rene Descartes plane. We also need to do for t, which is time. Next, we do something similar for the fields of other forces. We also need their kinetic energy in every possible direction. Wait. We know that if two photons head into each other, they will pass straight through each other. But if two gluons does the same thing, they will interact. We therefore need an extra term to describe the potential energy of that interaction, which we add the kinetic term. Here we see a connection to the classical Lagrangian with this kinetic and potential energies. The main indices that are here come from the complex symmetries of SU3 and account for all the different types of gluons. The bosons of the weak force get a term like this also, but its SU2 symmetry leads to a different behavior. The weak force also has a second kinetic term that looks like electromagnetism, a consequence of the fact that the weak force and electromagnetism are close relatives. These complicated kinetic terms are multiplied with themselves in a matrix multiplication because it turns them into the appropriate units of energy. All these kinetic terms are summarized with the F's representing the motion of bosons and their interaction with each other. The next term introduces some matter to our universe. The psi is the wave function of the fermion fields. There are 12 fields for the 12 kinds of fields so far so known. They are condensed together with one symbol. So what would this D thing anyway? The slash is a shorthand that Richard Feynman used because he was always tired of writing gamma D. Hats off to you, man. Where gamma is a series of matrices to ensure that everything stays compliant with general relativity. The D itself is made of two parts. We have a derivative which tells us the energy of the field as it changes. The part with the field of the bosons tells us how fermions are going to interact with the fields that preserve the symmetries of nature. It is the field that gives us the information on matter-force interaction. The part with electromagnetic field is equivalent to the piece that was added to the Schrödinger equation to ensure phase variance. We also have to add the pieces for the other fields also. Here, each field is preceded by a new symbol which represents the charge the field interacts with. Electric charge, isospin, and color charge. And the more complex the symmetry, the more the indices we need. Also next to the charges are the coupling constants, which represents the strengths of each interaction. Now let's proceed to the next term, this Hc thing. It has ghosts of particles that cannot be measured and ghosts of infinities that make no sense. So we need to get rid of these scary ghosts because they are not nice. If we are a copy of matter term but we switch the sign of every imaginary number, all these problematic ghosts cancel out. Actually, we need a better strategy here. Hc is the emission conjugate, which is the process of flipping the sign of imaginary component. We have so far created massless particles for our universe. To add mass, we need the Higgs field, which is dealt by the rest of the Lagrangian. This term describes the fermions interacting with bosonic field. The Higgs field is represented by the phi symbol you see there. The Y is the matrix with the square of the matrix of each different fermion. We still have to measure the particles' mass experimentally. There, the Hc introduces antimatter to our universe. It tells us how antimatter picks up mass from the Higgs field as does regular matter. So far, so on. The next term tells us how the Higgs field changes in spacetime and how it interacts with the massive bosons of the weak force. The last term refers to the potential of the Higgs field. The Higgs gets its own term separate to the other boson because it is special. This term represents the Higgs boson itself. And so we are done. We have created a universe with all the sonon particles.
Cisco Educational Premium is a section of Cisco Educationals with content that is not hosted here. There are episodes ranging from long to short videos. Remember those good old shots of ours? They are there. So, do we get there? Use the link on screen or in the description or in the pinned comment below. Enjoy yourself. And I will see you in the next episode of Cisco Educationals.